Have you ever heard someone tell you that you're looking for the path of least resistance? Well, what exactly does that mean? Stay tuned and we'll find out. Hi, and welcome back to the channel. If this is your first time here, I'm Robin DeMarco, the online physics teacher, and my passion is taking the mystery out of physics and helping you to supercharge your science education. In the opening sentence, I asked, what is the path of least resistance? And what does that mean? Well, let's start by looking at the term resistance. And resistance is defined as the opposition of a material to the flow of electrons through it. What? Let's take a little different look at it. If we look at the two pictures that here, which one would allow you to move the easiest? Correct, the one on the right-hand side would. Why? There's very little traffic involved. So what factors are going to help us determine how much resistance we have on that road? Well, we might consider, what are the conditions? Are the lanes dry, or are we plowing through a foot of snow? How many lanes are moving in the same direction we're going? And how long are we going to be on this road? We can equate this all to a current carrying wire. So what material is this made of? Some materials, such as copper, let electrons flow much easier than other materials do. And this gives us something called resistivity. We use the Greek letter rho to represent this. And the resistivity is the resistance of a 1 meter long conductor with a cross area of 1 square meter. We can find a table of common resistivities in various places. You'll find them in the CRC Handbook of Chemistry and Physics. Some reference tables include them as well. The next area we should look at is, what is the cross-sectional area of the conductor? Is it a very big wire, very small wire? And how long is this conductor? If it's a very long wire versus a very short wire, we're going to find very different resistances as well. All right, what I have here, besides a piece of cardboard, is I have two pieces of wire. And the first thing you'll notice is they're the same length. Now, the second thing you may notice is that the very thin one here, not only do I have the ends stripped down to just bare copper, but here in the center, I also have a piece of bare copper as well. Now, what we're going to do is we're going to use a multimeter, and we're actually going to film this. Now, the way the multimeter works is, if we have a complete path, what will happen is when we put the two wires together here, we get a reading. Okay, and that tells us that there's resistance in the wire. So we can actually measure this resistance. What we're going to do is we're going to measure the resistances of these two wires. So the thin wire here, what we're going to do is we're going to go from the one end to the center, and then we're also going to do it to both ends, so we get the entire length. And we're going to compare that value that we measure here for the resistance. There we go. We're going to do the same thing with the thicker wire here, but in this case, we're just going to go from end to end. Let's take a look at what we saw here. When we looked at thin wire, we found it had a higher resistance than the thicker wire. So what factors did we find here? We found that the longer the wire is, the higher the resistance is, and the thicker the wire is, the lower the resistance. We have an equation we'll use for that, and it says that the resistance of any object is equal to the resistivity times the length divided by the cross-sectional area. Okay, so what we're going to do here, we know that the resistance is equal to rho L over A. So in this case, what we have for rho, we're taking the resistivity of copper, 1.68 times 10 to the minus 8 ohm meters. And we're going to multiply that by the length. Now remember, the length here is given to us 45.7 centimeters, but we need it in meters. So that's going to be 0.457 meters. And we're going to look for the cross-sectional area, which is 1.0 times 10 to the minus 6th square meters. Now, as we do the equation at the top here, we're going to get 7.68 times 10 to the minus 9th ohm meters squared, divided by the 1.0 times 10 to the minus 6th meters squared. And that's going to give us a resistance then of 0.0077 ohms, or 7.7 times 10 to the minus 3 ohms. Well, that's it for this episode. If you haven't already downloaded your copy of the 15 tips on how to improve your science grade, that link is in the description below. I hope you found this video useful, and if you did, please consider giving me a thumbs up and subscribe to the channel, please. I post a new video every Friday, and hitting that notification bell below will ensure that you get notified the next time I release a new video. Until then, happy calculating.